Here we are given a pretty complicated reaction, and we are given a number of moles of phosphoric acid and a number of moles of aluminum carbonate, and we are told that it's going to produce a certain amount of water molecules, or liquid water. We need to determine what the percent yield of this reaction is. So if you recall, percent yield will be our actual yield, so what's being produced in the experiment, divided by our theoretical yield, which is based on the mathematics and the calculations with our balanced reaction equation. Once we know those values, we can do the ratio, get our percent yield. And we already know what the numerator is. Our actual yield is 44.3 moles of water. So what we need is to determine what the theoretical yield of water would be. Now, there are a lot of calculations out there that state that the percent yield should be done in grams. However, if it's of the exact same compound, water on top and water on the bottom, the ratio of masses and the ratio of moles would actually be the same. So since we're already given a value in moles of water, let's stick with the theoretical yield in values of moles. But there is a catch to this, because I stated that with a theoretical yield, we need to use a balanced reaction equation. So let's take a look at the information that's given to us in our reaction. Well, I have phosphoric acid, so if I look here, I have 3 hydrogens on the right-hand side and H3PO4, but if I look at my right-hand side, let me rephrase that, I think I might have said that wrong, I have 3 hydrogens in the phosphoric acid on the left-hand side. But if I look at the hydrogens on the right-hand side, I only have 2 found in the water, so this is unbalanced. So I'm just going to rewrite my reaction. I'm going to do it in a little bit of a better way so I can, be more organized when I do all of my calculations work. And the one way that I like to organize my balanced reaction equation is that I try to write all of my ions and elements directly below my arrow. Now notice I said ions. Now if you notice that a polyatomic anion repeats on the left-hand side and the right-hand side, you can actually balance that ion rather than having to separate out all of your elements, which is actually really handy for us. Because if you notice, I have hydrogens on the left-hand side and the right-hand side, but I have that PO4, I have that phosphate ion on the left and the right. So rather than having to break down those oxygens and the phosphates, I can actually just leave the phosphorus atoms, I can leave the PO4 separate, which is really convenient for me. On the left-hand side for aluminum, and then I cannot do the same thing for carbon for the CO3 versus the CO2. So I have to break down the carbon and the oxygen that way. So if I take a look at the left-hand side, I have 3 hydrogens, I have 1 phosphate, 2 aluminums, 3 carbons in the CO3, because I have this set of parentheses right there. By saying I have CO3, what I have is 3 carbons and 3 times 3 oxygens, or 3 carbons and 9 oxygens in that. So you always have to pay attention to the subscript in the parentheses. That subscript outside of the parentheses accounts for every atom that's in there. Which means for the oxygen on the left-hand side, I'm only going to use 9. I'm not including those 4 from the phosphate ion because I'm keeping that phosphate together. Now, on the right-hand side, I have 1 carbon in my CO2. I have 2 oxygens in the CO2. I have 2 hydrogens in the water. I have 1 oxygen in the water. I have 1 aluminum in my aluminum phosphate. And I have 1 phosphate in my aluminum phosphate. So notice how many I have on the left-hand side and the right-hand side. And notice I will have 2 separate sources for my oxygen on the right-hand side. So it's always nice to pay attention to that. So if I take a look at everything, one thing that really stands out to me a lot is the unbalancing of my aluminum and my carbon. So I'm going to focus on the aluminum first because those tend to be the more complicated of the molecules. So since I have 2 aluminum on the left-hand side, I will put a 2 in front of my aluminum phosphate. So that 1 now becomes a 2, and the phosphates now also become a 2. So from that, I really don't have a solid plan except for, well, the carbons are a little out of balance. I have 3 carbons on the left-hand side, so why don't I go ahead and put 3 in front of my carbon dioxide? So the carbon on the right-hand side becomes 3, and 2 of the oxygens now becomes 2 times 3, or 6. All right, so let's see here. All my phosphates are a little unbalanced. I do have 2 phosphates on the right-hand side, So why don't I go ahead and put 2 phosphates on the left-hand side by putting a 2 in front of H3PO4. So my hydrogen now goes from 3 to 6, and my phosphates go from 1 to 2. I have 6 hydrogens on the left, only 2 on the right, which is nice because I only have water left that I haven't touched yet on the right-hand side. So I'll put a 3 in front of that. So the 2 on the right-hand side now becomes 2 times 3, or 6. And now my oxygens go from 1 to 3. And 6 plus 3 is equal to 9. So I didn't actually have to touch my aluminum carbonate. So my Al2CO33, I didn't have to touch the coefficient out in front of that. Now, to make sure that this is properly balanced, we need to make sure that all the coefficients are at a simple whole number ratio. So I like to just rewrite my ratio value. So I have a 2, a 1, a 3, a 3, and a 2. So what I just wrote down there is just the ratio of all of my stoichiometric coefficients. And notice I can't really divide that by a number that's not 1. I can't divide all of them by 2. I can't divide all of them by 3 and still have a whole number ratio. This means I have the simplest whole number ratio for this balanced reaction equation. So ahead of time, I went ahead and rewrote my reaction equation so I can save some space for the actual calculation work. Now that I have it balanced, I now will use this to determine my theoretical yield. But another little snag is hit. You see, I have a number of moles of my phosphoric acid and a number of moles of my Al2CO33. I don't know which one to use. One of them has to be in excess, and the other one has to be limiting. Or maybe they're both being completely used up. I don't know. Now, since they're both in moles, I'm sure that some people have the instinct of going, okay, well, I have more moles of the phosphoric acid than I do my Al2CO33, so that should mean that my H3PO4 should be in excess and the other one should be limiting. And that's not the case for limiting reactant. In order for us to determine a limiting reactant, we want to figure out how much of a particular product one could make versus the number of the exact same product the other one could make. Whichever one has the least amount of that product produced, that's our limiting reagent. Let me explain. Now, we know that we're dealing with producing water. So let's find the limiting reagent in terms of moles of water. First, we'll start with 41.4 moles of my H3PO4. And based on my mole to mole ratios in my balanced reaction equation, I have 2 moles of H3PO4. And I need those 2 moles to produce 3 moles of water. So I'm just going to take the number of moles of H3PO4, multiply it by that mole to mole ratio from my balanced reaction equation, and get 62.1 moles of water. So this is the maximum amount of water I could produce if all of my H3PO4 was used. I will now do the exact same thing for Al2CO33. So 37.0 moles of Al2CO33. From my balanced reaction equation, I only have 1 mole of Al2CO33 that could be used to generate my 3 moles of my water, which will give me a value of 111 moles of water. And when I look at the comparison between the top value and the bottom value, my bottom value is actually bigger than the top. This means that my top value, my H3PO4, will be my limiting reactant, or my LR. And that also means that my Al2CO33 is going to be in excess. But the best part is that once you note your limiting reactant, you use that value to determine what your theoretical yields are. And I just found the theoretical yield of my moles of my water because that is the most amount of water I could produce. Because once I go higher than 62.1 moles of water, I actually can't. Because all of my H3PO4 is going to be used up. I cannot produce any more than 62.1 moles of water, no matter how much of my Al2CO33 I have, which is great. I've kind of reached this peak. So my percent yield will be my actual yield given earlier at 44.3 moles. and I'll divide it by my 62.1 moles, both of my water. And I get a value of 0.71336554 to 3 significant figures, or 71.3% yield. So always remember to double check any reaction equation given to you. Always check to see if it's balanced. Also practice balancing reaction equations, because if you notice any polyatomic ions that repeat on the left and the right hand side, you can balance that polyatomic ion. It will make your life a little bit easier, because who wants to count all of the oxygens? Yeah. So, and lastly, remember, when you determine the limiting reagent and the excess, you always want to pick one product to focus on and determine how much of a reactant can maximally produce that one product, and then just compare those two values. Because once I now know the number of moles of water that could be produced from either, I can determine what my limiting reagent is from there.